Okay, so for this part here, I just wanted to show you guys diagrams for what is going on for ionic radius size. And keep in mind here that it is different depending on whether the element is a metal or a non-metal. And I'm just going to go through and draw out the first example that I gave you guys in class for a metal ion versus just a regular plain metal. And initially, it's going to look something like this. I'm going to do an example, and I'll use sodium ion as our metal ion here. And if you compare this in size to the size of just pure sodium with no charge on it, kind of looks like that. And here's what you guys want to remember. So the sodium to become a sodium plus ion, there was a change in electron that happened. And here specifically what happened was that we lost one electron from sodium over to the sodium plus. Now, if you think about what electron it is that ended up getting lost, it always is going to have to go back to our valence, which is 3s1. And when the sodium plus, or when the sodium lost that 3s1 electron, it no longer has any electrons on the third energy level. And we actually go back down to energy level 2 here. And because we lost an energy level, that explains why the size of the Na plus is so much smaller than the Na. Again, we went from energy level 3 down to energy level 2 when we lost that one electron. And remember that sodium, by losing that one electron, it now has an ending configuration of 2p6, just like a noble gas, which is what they wanted. Now I'm going to do the second example here, which is taking a look at not a metal ion this time, but this time we're going to look at a non-metal ion radius to see if there's anything really different from the two. And you kind of already know that there is because it's written out here in the notes for you. So we have our non-metal ion radius. So let's take a look at something like chloride this time. We'll say Cl, the negative charge, so that's our non-metal. And this guy here is a lot smaller than regular chlorine. Okay, so we have regular chlorine in comparison to chloride, and you could tell that chloride definitely has a much larger radius than chlorine here. And an easy way to remember trend-wise what's going on is that chlorine, to turn into chloride, we actually gained one electron here. So there is a gain of one electron that happened from chlorine to chloride, so Cl negative. So if you guys just stated this as a rationale for why this happened, it's not telling the full story. So yes, chlorine did gain one electron, but it doesn't explain why the radius for the chloride ion is so much larger than the chlorine atom. And here, the best way to actually explain this is to go back and talk about protons. In our chloride ion, we have 17 protons, and we also have the same number of protons over here in my chlorine atom as well. So chlorine also has 17 protons. So even though there is a difference in the number of electrons, the protons will always stay the same. Otherwise, if you change the number of protons, it would be a whole other element. Now, in this chlorine atom, we have 17 electrons. In this one here, we have 18 electrons because we gained one. And what's going on here is, even though the effective nuclear charge is the same, they still have 17 protons in each of them. By picking up an extra electron, it turns out that these protons are not able to attract the 18 electrons as well as it did with the 17 that it had earlier, because you have one more electron than the protons. So because these protons are not holding on to the electrons as tightly as before, the electrons are able to kind of move out a little bit more. So you could see here that our radius has definitely increased because we just added on one extra electron. But it threw this off, And basically, again, the rationale for why this happens is that these 17 protons do not have a very tight hold on the 18 electrons because one was added on, and then the electrons move out a little bit more because there's less attraction. Another way that you guys could see it explained right here in the notes as well is by adding in an extra electron. And we know that it didn't go up or down energy level. This is still taking a look at the same level of energy, but by adding in an extra electron, now what you've done is you've increased the repulsion between the electrons. The electrons are like, hey, there's one more, and they're going to want to try to space themselves out a little bit more, and thus they move out. And again, they're able to move out because the charge in the middle hasn't changed. The effective nuclear charge is the same, but then the number of electrons is different. And that's it.